Alrighty, well, everyone, welcome to the final Planetary Sample Science Seminar Series of the year. So we've made it, and today we have a really, really special guest. I hope everyone enjoyed their Thanksgiving here in the States, and for those of you that are across the ponds, happy holidays and everything. So today we have Ryan Ziegler, who is from the Johnson Space Center. So Ryan got his bachelor's in geology from the State University of New York, Potsdam, and his master's and PhD from Washington University in St. Louis. He has kindly asked for me not to say the years in which he's got these degrees, but after his degree, he stayed on at Washington University working as a research scientist, specializing in the petrography, geochemistry, and provenance of small rock and glass fragments found in lunar regolith, as well as the study of lunar meteorites. Currently, Ryan is the Lunar Sample Curator at NASA, a post he has held for the past 12 years. He also manages the X-ray Computed Tomography Lab for Astromaterials at the Johnson Space Center. And today, Ryan is going to talk to us about the Apollo Sample Suite, its diversity, utility, and how it has been curated historically in recent activities and in the labs. And finally, he's going to give everyone a quick tutorial on how to write up a lunar sample request. So, Ryan, without further ado, please take it away.
Thanks so much. I'm excited to be here today. I'd like to thank Chip for inviting me to come and give this talk. I mean, I'd like to. If I was doing this back in July when I agreed, I definitely would thank him. Now I'm not sure I want to thank him, but excited to talk to you all today. You kind of already said what I was going to talk about, and you'll notice that I've already changed the project or the talk since I answered your email yesterday, and I don't think I'm going to talk about how to write a sample request today, simply because I don't believe we're going to have time. And I gave that talk last month, and I'm pretty sure it's online. So, but folks can ask questions about it. So what I'd really like to focus today on is, the Apollo samples themselves, the complexity of the Apollo sample suite, and then sort of spend some quality time on how we curate them and over the last 5 decades, and how that's enabled a wide variety of research. And then in the second half of the talk, we'll talk about ANCSA again, but I want to sort of take it from a slightly different point of view, where I want to talk about the things that we either had to relearn how to do or learn how to do, and how that's helping us get ready for Artemis. And so I think I'm contractually required to use this as my first slide in all my talks, or one of my first slides. We're obviously going to talk about the Apollo samples today, which are, in my completely unbiased opinion, the best samples. And so I'm excited for us to talk about just that. But it's important to realize that they are just one of our 9 different collections. And while we're going to have a nice chat and an important scientific discussion about the Apollo samples, we really could have this discussion about any of the collections we have. And so it's important to know that this is part of a larger whole, what we're doing for Apollo. So if we're going to talk about Apollo, you really need to start with the fact that it was a crewed mission. Now, this might seem like a shameless attempt for me to show rockets because I like rockets. That's partly true. But it turns out that what really sets the Apollo missions apart from all of the other astromaterial sample return missions is that they were collected by astronauts. And so it turns out astronauts are incredibly useful when it comes to collecting samples. If you look at these pictures, which I mostly picked because I thought they were pretty, but they are also showing a wide variety of different ways that the astronauts are interacting with the lunar surface and to collect samples. So they're collecting rocks, they're collecting regolith, they're collecting core, they're collecting rake samples, they're doing scientific experiments, they're driving the rover around, they're getting sealed samples. So there's this huge diversity of samples that are in the Apollo collection. That's what we'll talk about for the next few slides. But all of that is enabled by the Apollo astronauts. And they were doing this on the course of days, not years, like many of the sample return missions take. Now, I understand the differences in budget and scope. I'm not trying to start a fight about whose mission is best, even though ours is. The point here is that, without the Apollo astronauts without the Apollo astronauts, the discussion we would be having would be very different, as I believe the Apollo sample suite would be much more limited. And so here you can see near side LROC WAC mosaic that I've stolen, and I've superimposed the approximate. I don't want emails about how my dots are in the wrong place. The approximate location of the 6 Apollo landing sites on the near side of the moon. And the point here is to show that while the Apollo sample sites are not a perfect representation of the, she'll turn that off, uh, geologic diversity on the moon, they are a pretty good approximation. You've got the Apollo 11 and the Apollo 12 sites that landed in the Mare. You've got the Apollo 16 site that landed in the true highlands, the Apollo 14 mission that landed in the highlands-esque Fra Mauro Formation, which is really a basin deposit, but it's not a mare. And then you have the Apollos 15 and 17 missions that landed up here at the junction between the Mare and Highlands. So you've got a pretty good representation of Mare and Highlands within the Apollo sample suite. Now, if we start to look at some of the different rocks that were brought back from the moon as part of the mission, here are some of everyone's favorites, the very well known. You've got the anorthosites that represent one of the major components of the highlands, we think. You've got the basalts that obviously compose the mare, and then you've got a few specialty samples like the one troctolite we have from the moon, 76535. And so, there are a lot of different igneous rocks that came back from the moon, but actually the vast majority of samples that the Apollo missions collected were polymictic breccias, more like this, and other even more complicated and ugly samples. And I call it ugly to look at, perhaps, or perhaps for a grad student to study, not that I still have scars, but they're really important samples because every one of these polymictic breccias is a mixture of hundreds, really thousands of other rock fragments, and each of them has their own story. And so there's this incredible diversity of rock samples that were collected across the 6 missions, but rocks are only one part of the story, as fully 1/3 of the mass that was collected were regolith. And so we think of the regolith typically as, fine grained powdery material as an average grain size of 50-ish microns. And, you've all seen the iconic boot print on the moon. But mixed into every regolith sample are rock fragments in different size, 1 to 2 or 2 to 4, 4 to 10 millimeters. And each one of those rock samples, again, has its own story to tell. And then, there were drive tubes and drill cores, and they drilled almost 3 meters deep, 2.7, 2.8 meters deep on the Apollo 17 mission. And so the point here is that across the 6 sample sites and the large mass, almost 400 kilograms of material that was returned, you have this wide variety of types of rock, rocks, cores, and samples, rocks, soils, cores. But then within each of those rock types, you have an even wider variety. So within the regolith, you have bulk regolith samples, you have skim, basically surface regolith, you have trenched regolith samples, you have shaded, you have rake samples, fillet, you have all these different types of regolith samples. And while most of them are bulk regolith, each of the different subtypes of regolith or rock allow you to address different scientific questions. And one of the really nice things about the Apollo collection is that they are pristine. Now, pristine does not mean exactly like they were on the moon, and we'll come back to what I think pristine means when we talk about how they're curated. They also have really good geologic context. And where that sets these apart is from the lunar meteorites, because you have to remember at this point, we have more mass in lunar meteorite collection than we do in Apollo. I forgot to look before I did this talk today, but I think it's up to 600 kilograms and more of lunar meteorites, and representing at least 400 different stones. And so those are great, and they all have a story to tell, but they lack the geologic context that the Apollo samples have. And so the Apollo samples allow you to sort of address different questions than you would with the lunar meteorites. Now, we don't have time, or really the interest, I think, for everyone to sort of delve into the details of each of the Apollo sites, but I thought we'd spend a little time looking at Apollo 17, which is everyone's favorite mission. I don't know if Jack's on, but just in case he is, I'm going to say that. Here you can see sort of an oblique view of the Torres-Latro Valley, where the astronauts came in and landed on the Mare Fill at the bottom of the valley, somewhere over in here, so that I don't get emails from NOAA. And then the point I want to show here is that there is a diverse geology here at the Apollo 17 site. You've got the Mare Fill in the bottom. You've got the highlands, really basin deposit massifs in the south and the north. You've got the sculptured hills. You've got the landslide deposit. So again, as we delve, in more detail at just these one sites, you start to get an idea of the different things that were sampled by the Apollo missions. And so here you can see sort of a planar view something I stole from the folks at ASU and didn't reference them again. So shh, don't tell them. But what this is the traverses of the Apollo astronauts on the 3 different EVAs, and it shows the different materials where they're out on the valley floor here on the basalts, and then they come over to the South Massif and the landslide deposit, and they go up to the North Massif, and you've got the boulders that are rolling down the hill. And so each one of these numbers, where they are their primary sampling locations, has its own, sort of detailed geologic story. And probably the prettiest one to look at, and maybe the most important, we can argue about that, is here at Shorty Crater at Station 4, where you have this really nice, young, sharp crater. And this, they collected a fair number of samples here. You can see some basalts, you can see some regolith samples. What would really set this apart was, of course, this is where the orange soil was found. You had the pyroclastic glass beads that were part of the basaltic valley floor. And so, across the Apollo 17 mission, they collected almost 115 kilograms of sample, just over 750 different generics. And again, just like the previous missions, or the previous slide where I was showing all the missions together, you've got this wide variety of basalts wide variety of rock types and regolith types. Great. So now we've collected the samples. I need a sip of coffee because clearly I need to talk faster. All right. So let's talk about what happened to the samples when they came back. So the original home for the Apollo samples was the Lunar Receiving Lab, the LRL. It was built in the mid-1960s and finished in 1967. Here you can see a picture of it, presumably just not too long after it was completed. It doesn't even have sod laid down. And now this was designed as a quarantine facility, because remember, in the 1960s, we didn't know whether there was life on the moon or not, and we didn't know how life on Earth was going to react to life on the moon. So out of an abundance of caution, probably, they designed a quarantine facility, a negative pressure clean room that's similar to a BSL-4 facility nowadays. I'm not trying to start a fight about that. I understand that a modern BSL-4 lab is considerably more rigorous in its quarantine than what we had back then. This is what we had at the time. And so you had the sort of the high rise over here that housed the samples themselves, as well as some of the associated science labs to go with it. And then you had the administrative part. And so this was the home for the Apollo samples for the first 3 years. A lot of the work that got done in here was related to were the samples, safe to take out of quarantine. So they were feeding them to animals, all manner of animals, and exposing animals. And apparently some Apollo 12 scientists got exposed as well, to check and see if they were going to wipe everything out, which they didn't. That was good. That was positive. They tried really hard early on to work under vacuum, especially on Apollo 11. And that quickly proved to be untenable. They kept losing the vacuum and flooding the chamber with Houston air. And so they realized that rather than work in a tenuous vacuum situation, it was made more sense to switch to nitrogen purge conditions. And we'll see more about that. And so once they realized that, there wasn't life on the moon, there was no longer a quarantine worry, which is really after the Apollo 12 mission, but they kept the quarantine in place till after Apollo 14. By the time 1972 had moved around, they had actually moved the samples out of the LRL and then into 6 short laters. So the current home for the samples is here. This is Building 31 North, which was completed in 1978, and it's been the home for the samples ever since. And so you're like, wait a minute, a lot of time happens between 1972 and 1978, and I'm not great at math, but like 6 years. And so what happened to the samples then? And so that's something we don't like to talk about, and I get yelled at by Andrea when I do, but jokes aside in my bullets, between 1972 and 1978, there was a temporary facility that in what is now the Meteorite Lab. And so for what I'm going to show you for the current home in Building 31 North, that was essentially the same type of conditions that it was stored in from 1972 to 1978 in what's now the Meteorite Lab. So we're going to skip that part. Also, I couldn't find very many good pictures. But the Building 31 North, the current and probably forever home, it seems, for the samples, is designed to be particularly robust. It is hurricane resistant. Hope I didn't write proof. It's rated to withstand a Category 4 hurricane. It wasn't just designed to be robust in terms of protecting the samples from the environment. It was actually designed by almost said a suite, but designed by a panel of scientists to be minimally contaminating to the samples. And so they were very thoughtful in their collection of materials that they decided to incorporate into the collection. Incorporate into the building. And so, and that's where the samples have been stored ever since. And now not all of the samples are stored here at JSC. We do have a representative suite of samples. It's about 15% of the mass that is stored in an offsite location. Originally, it was stored in a bunker at Brooks Air Force Base in San Antonio. And then when they closed that, we moved it to our secret facility that's, out at White Sands. So shh, don't tell anyone. I'm not telling you where at White Sands. Turns out there's a lot of stuff out at White Sands. So, but let's talk more about how we take care of the samples here at JSC. And so one of the most common questions I get in doing talks or tours and stuff is how much of the samples do we have left? And it turns out we have about 83% of the Apollo samples by mass that remain pristine. What does pristine mean? Well, it depends on who you ask. And so for me, and for the way we define it here, is that pristine samples have been kept under nominal storage conditions since they were returned, and we understand their detailed exposure history since they came into our possession. So what are the nominal conditions? And so, well, first of all, they're kept in clean rooms. So we have a suite of ISO 6 clean rooms. It's class 1000. So here you can see me with the vault for scale, or maybe it's the other way around. I'm not sure. And a picture on the bottom of Andrea and the other processors in our pristine vault. And so these stainless steel cabinets are nitrogen purged. There's 316L stainless steel in the cabinets, and the samples are stored and sort of inventoried in our vaults in these containers. So when you ask for a sample, we find out where it is in our database. We come back here, we pull it out, and then we transfer it over to our processing lab, which looks a lot like our vault. And again, it's a series of these nitrogen purged glove boxes that we use to manipulate and process the samples from their larger form into the subsamples that y'all are going to get to do your scientific studies. So we're very careful about what materials we allow the samples to be around and particularly to come in contact with. So I think I mentioned the cabinets are 316L stainless steel. They have glass, or in some cases polycarbonate, because money was short in the 80s, windows in them. They have largely neoprene gloves. But we don't actually let things like glass or polycarbonate or neoprene come into contact with the samples. The only thing that are allowed to come into contact with the samples are basically 316 or 304L stainless steel, 6061 series aluminum foil, a couple different kinds of Teflon. And then we have a few specialty hard plastic containers we use for folks who are worried about metal contamination in their samples. And so that's really the only things that are allowed to touch the samples. So now these are our normal processing cabinets here, but then we have some specialty cabinets. This is our core processing cabinet. It does have gloves on it now. Apparently I don't have a picture of it with gloves. And so you get the non-gloved version. We have a bandsaw cabinet. So we have the ability to both cut large rocks under a nitrogen environment. We can process and dissect cores. We're going to talk a lot about that later under nitrogen. And then everything I've been talking about is what we consider for nominal pristine samples. But as those of you who have samples or have worked on samples know, that everything we do is a loan. And so we loan samples out to you, and when you're done with them, you send them back to us, and we hold on to them and we try to reuse them. And while you all fill out, because everyone does, I'm looking at a few people, the sample history report for what you did to the samples, since, well, sometimes people forget things, and sometimes there are things that were done to the samples that just aren't compatible with being put back into the pristine collection. In fact, most of the time, we have an entire separate vault and set of labs that we use for the return samples, where we process things in air. And that's an ISO 7 lab. And I didn't put pictures of those in, but oops. And then I think I've mentioned this a few times now, but like the handling history and how we move the samples around, what has happened to them, where it happened, when it happened, all of that we keep careful track of. And then we have a few other instruments, and we'll talk about those later. So usually that's where I stop. Usually when we're talking about how do we store the samples, we just talk about where the samples are physically stored, but that actually does a little bit of a disservice to what goes into doing this. And so these are very pretty pictures. You can see our you can see the different types of infrastructure that we use to keep the samples clean. So, I mean, the shiny clean rooms are the most obvious example of what's protecting the samples, but those clean rooms don't work without the underlying physical plant that supports them. And so we have 10 different HEPA filtered HVAC systems throughout the building, 3 of which are dedicated solely for the Apollo labs to provide clean air to the labs. We have to keep the power supply steady. And so I think those of you who got an email from me or sent me an email a month ago would have noticed we had a big power outage as we were hooking up our whole building generator, our brand new whole building generator into the system, so that now we have a more consistent power supply. We have that 17,000 gallon tank of liquid nitrogen that you see there, and we use the boil off from that as the inert gas, or almost inert gas, we use to keep the sample safe. And that, the gas itself is a special type of nitrogen we have trucked down from Dallas that they use like when in the semiconductor industry to try to keep the impurities within the nitrogen down. And then, of course, we have our ultra pure water system, which is how we clean our tools, how we clean our cabinets, how we use the things we need to put around the samples and keep them clean. And so it's probably more work to keep all of these going and keep them supporting the labs than it is to actually run the labs themselves. And so it's worth talking about. And then the other thing that I think is lost sometimes is how much work goes into being able to demonstrate that you're actually keeping the samples clean, or that you're, keeping the samples as clean as you say you are. So, I said we have an ISO 6 clean room. We aren't officially ISO rated. We don't go through that process because it's sort of onerous. But every week, someone goes in with a particle counter and checks to make sure that we are, within the allowable number of counts. And if we're not, then we try to figure out what's wrong and address it. The ultra pure water system has to be monitored every day. If our water isn't, clean enough, if the mega ohms isn't low enough or the total organic carbon isn't low enough, then we're not able to clean, and then everything grinds to a halt. All the different labs, we have a whole bunch of technicians who both clean and physically maintain the labs. Shout out to Myra, who does most of the hard work cleaning up after us in the Apollo labs. Without them, the labs don't stay clean. We get nitrogen delivered every week, pretty much. Every truck comes with a certification of analysis on it so that we know whether or not the truck is good enough. And if it's not, we don't accept the truck. And then we make them bring us a new one. We actually now have the ability to measure the nitrogen gas composition in real time ourselves. And that's, really helpful for us. We actually measure the amount of oxygen and water in the cabinets 4 times an hour. Not every cabinet 4 times an hour, but every hour we measure 4 cabinets. And so we sort of cycle throughout the day. We even keep track of things like the nitrogen gas composition in the lab. And I think I made that sufficiently small so that people can't see the numbers. That was on purpose. But you can ask questions about it later, and I will pretend I know the answer. And then, of course, we periodically keep track of what's how clean the cabinets are, how clean the labs are by doing these third-party chemical tests for each. And so it's a lot of work to make sure you keep track of, how clean the samples are. So that is how long have I been talking? Longer than I thought. 13-minute version of how we keep the samples clean. And so, what do you think? So when the Apollo samples are 55 years old now, and why are we still studying? I get that question all the time. We don't really have time for it, but I'm going to tell a funny story anyway. When I started grad school at Washington University in St. Louis, I sat down at across from Larry Haskin, who was one of the original lunar PIs. And I think I was still Perspective at the time. And I asked him what he did, because, I don't do homework. And he said, we study Apollo samples. I'm like, well, that's been 25 years. Why are you guys still studying them? That was not a great way to start a conversation with your future advisor. So I almost got kicked out of grad school before I started. But no, it's a legitimate question, and we've been studying the Apollo samples for 55 years. Are people still studying, or are we still getting a lot out of them? And I think the answer is an unambiguous yes. And so here you can see the number of samples we've allocated per year going back to 1984, which is conveniently when I have convenient data for it, as well as the number of requests. And so we've had almost 3,420. I should have updated this morning. The number is actually 3,450 because of the fall requests, but we're averaging 60 requests per year, and we're still averaging almost 60 requests and 600 samples per year for the last 12 years. I mean, we had a little bit of a downturn for the pandemic, but we are starting to creep back up towards the pre-pandemic numbers. And so lots of people are still studying the samples. And so what has been done with the Apollo samples over the last 50 years? Now, it's hard to summarize 3,400 requests and 55 years of science in one slide, but here's my take at it. Now, I'm not trying to talk about all of these in detail. I mean, you get people who are more versed in this than me to come in and give important, better talks on the giant impact origin of the moon and stuff like that. But what I'm trying to show with these, the series of slides is the breadth of things that have been talked about on the moon. And these are just a drop in the bucket of the big picture things. And so, obviously the samples from the moon have taught us a lot about the moon itself. And since the moon came from the Earth, we taught us about the Earth-Moon system. So how did the moon form? Giant impact origin, magma ocean on the moon, things like that. A better understanding of the geology of a planet that's not the Earth. The place that we know the most about is the moon. Now, you might not like the magma ocean, and that's great. And you might want to argue that that's not what really happened, but it just replaces the picture on here with how a planet formed and how it evolved. And so, how it formed is great, but how it's been modified is also important. And so, apologies to Harry for stealing his map that I think about 10 years of work went into, just thrown in on my slide. But, understanding the absolute ages of the surface of the moon through crater counting is only possible because we have the samples that have come back from known locations. And while, the numbers are the best for the moon, when you see people talk about the ages of craters on Venus or Mars or, absolute ages, then all of that is tied back to the crater counting record from the moon. Similarly, as we understand how space weathering on airless bodies works, a lot of it is tied back to what happens on the moon. It's less and less the case because now we have Hayabusa and OSIRIS-REx samples. So we have samples back from other airless bodies, but the original understanding of how airless bodies, space weathered, how they evolved came from the lunar samples. And it's sort of obvious to think, okay, we know about the other terrestrial planets and the asteroid belt from the Apollo samples, but we can actually say something about the outer solar system as well. Now, I don't know whether you favor the cataclysm, whether you want a slow and steady decline of impacts or not, but really, again, doesn't matter because whatever model you're going to, that is going to be made in order to explain how the solar system formed is going to have to account for the ages in the Apollo samples. It's not the only data point, but it's an important one. So if you want the NEAS model or the Grand TAC model, or I don't know, I've lost track of what all the models are, the ages of the Apollo samples have played an important role in helping with that. Sorry, I'm just making sure that y'all can hear me because it's weird to talk for 40 minutes and not hear another peep. Okay. Sorry, I lost my train of thought. Oh, right. You can actually, extend the study beyond the solar system itself out into, understanding how our solar system's place in the larger Milky Way galaxy and how it moves around. Sorry, I'm going too slow and I have to speed up a little. And so it's used as more than just a primary science tool. It's a calibration for other methods. I've stolen the thorium map from the lunar, oh my God, I blanked on the Lunar Prospector mission here, but I think that every single remote sensing or orbital mission to the moon has used the Apollo samples to make their data better, whether it's GRAIL or LRO or Clementine or, Kaguya, they all have used the Apollo samples and what we know about the surface to improve their data. And we're also using it to get ready for future missions. Here you see a picture of an astronaut covered in dust. Turns out that dust is not great to breathe in. So as they get ready to go back for Artemis and longer term habitation of the moon eventually, then understanding how the dust affects people is important. And this is one of those things where a simulant doesn't really cut it, and so you need the samples themselves. Okay, so that's the first half of the talk, which took more than half the time. So take a deep breath and get ready because now I want to talk about ANCSA. Now, I know Chip already gave an ANCSA talk in one of these, I think it was like a year ago now. So since I'm confident no one remembers anything for a year. I don't feel that bad. Although I straight up stole this slide from Chip. So I don't really want to spend a lot of time, because we don't have a lot of time, talking about the underlying reasons behind ANCSA. That's a different talk. I just want to talk about how we used how ANCSA affected us and what we did with it. And so just real quick, so that everyone knows what we're talking about. This is the Apollo Next Generation Sample Analysis Program. And it was essentially at its core, we opened 3 previously unstudied samples. And so we had a sealed drive tube, core sample vacuum container that we had to extract the gas out of and then extract the material out of. We had an unsealed drive tube, and then we had a frozen sample, as well as some other frozen unexamined sample, as well as a few other frozen samples. And so I want to talk to you about what it took for us as the curation office to get ready for this. And so, there were quite a few things that, as part of ANCSA, that we had to either relearn how to do because we hadn't done it in a long time, or had to learn how to do because we'd never really done it and certainly not as part of a preliminary examination like this, or characterization is probably a better term. This isn't really a preliminary examination, it's more of a characterization. So we'll talk about these one by one as we go through. So the first part was we had to remind ourselves how to get the sample out of the drive tube. And, this was not new. There's been, I think, 21 different core sample vacuum, there's been 21 different drive tubes that have been that were collected, of which 17 have been extruded and examined, but we hadn't done it since 1993. I mean, that's a long time. This is more than 25 years. Now, luckily, we still had Andrea, and Andrea was the last person who was trained in 1993 to be the future of core dissection. And so now we had her teaching everyone else. And so we had to make up a simulant. We had to get the equipment out of storage, because it had been in storage. We had to machine some parts that had either been lost or mostly had corroded or had contaminants on them. And then we had to sort of build ourselves a way to practice without making the lab and the cabinet itself dirty. And so here you can see the erector set, the really actually quite a nice cabinet that they built out of plexiglass, and everything about it was pretty high fidelity. And then they spent weeks and months practicing what it was like to extrude the soil and get used to handling. Because remember, this is one of those things that you only get to do wrong once. I mean, if you extrude this incorrectly, you lose the stratigraphy, then, well, that's a whole lot of work for nothing. And so this is how we prepared for 73002 for the first one that was extruded. And then as we got to the second time we did this, 73001, a couple years later, we were able to add higher levels of fidelity and use, an actual glove box. And here you can see Juliana and Andrea as they do another round of training. And then, all of that prepped them really well for what it was like when they did the real thing. And so here you can see the actual laboratory. You can see the core sample processing cabinet now with gloves on it, although they're covered up. And then you can see, a few snapshots of the process. And, the point here is not to talk about the details of how we extruded the core, but to show that the hours and hours of work and preparation paid off, and that even when unexpected things came up, as we were trying to get the materials out of, especially the core sample vacuum container, it all worked out well. And you can also see the grand sum of my help with the extrusion process, which was to look over Andrea's shoulder and tell her she missed a spot. And so I'm really brave when people are unable to hit me. So, but again, it all worked out well, and they were able to successfully extrude both cores. You can see the 7.3. These are both 73001. Two different views of 73002 and the team of folks who did it. And then you can see that they started the processing here. This was a time-sensitive analysis that was taken because, they wanted to look at the organics. And so we got that sample off to Jamie Elsula as quick as we could once it was extruded. And then after that, we started the more systematic process of dissecting the core, which is, every 0.5 millimeter of interval, you use a small spatula and you start to outline it. You can see the dashed lines where they make, and then they're scooping out the material. And this schematic on the bottom shows how you plan ahead for things. And so Jamie wanted to look at the darker, more space weathered material versus the not space weathered material. So you had to be flexible in how you dissect the core, so that, you're not just doing a straight line across at all times, and then trying to coordinate the particles that Barbara wanted to get so that her samples were more directly comparable to the work that Jamie was doing, Case Walton, and they wanted to look at the exposure history of the samples. And so you can see where we tried to do sub allocations from the top, trying to do 2 millimeter wide scoops. Turns out doing 2 millimeter wide scoops with a spatula that's 2 millimeters wide did not work as perfectly. And so that was an important lesson learned for the next time. And so, so here's another view of how each interval is sort of scooped out and separated and then run through a sieve, and then all the different size fractions, 1 to 2 millimeter on the bottom row, and then 2 to 4 and 4 to 10 on the top. And you can see that, there were 206 intervals. So we had over 600 separate bulk samples, and then 350 of these large particles were all separated out and then bagged individually. Why did we bag them individually? We'll come back to that in a second. So we relearned how to extrude and dissect cores, and that went really well. And then we had to figure out what comes next. And so what came next for us was, we didn't do this completely blind. We had the CT scan. Now, I think if you've seen me give a talk over the last few years, you've already seen this slide. And so we took the 73002 and 73001 drive tubes off the UT Austin, where they have a really good X-ray computed tomography laboratory, and we worked with them to take these continuous core scans of the drive tubes. And so we used these in a reconnaissance sense to understand the nature of the materials inside, and it was important for a whole bunch of reasons for us as part of the curation process. But you also have this really nice permanent record of higher resolution data that was available for scientists in the future. And so it was actually more important than just like, okay, there's no sharp rocks near the edge, we're pretty sure we can extrude this without messing it up. Scott worked with Scott Eckley, who runs the CT lab here at JSC. He worked with the processors who were getting ready to dissect each of the different intervals and made these really nice scans with them so that they could understand, as they dissected down through the first interval and then the second interval and the third interval of the first pass, what material were they likely to get out? And then they did this for all three of the passes. And so these became a really important guide for the processors and Juliana as they were trying to dissect this to make sure they didn't run into anything unexpected. So the CT scans really became core and super important to what we were doing. I think I know how. And I showed you those bagged particles before as well. And so for the 351 greater than 4 millimeter fragments that were separated out, each one was scanned individually, bagged under nitrogen conditions. So we were able to keep them pristine, except for the fact that, yes, they have now been exposed to a significant amount of radiation. So their radiation record is reset, but we were able to keep the samples otherwise chemically pristine and understand for the 350 particles, which ones are basalts, which ones are regolith breccias, which ones are agglutinates, and everything in between, and then reconstruct. What is going on? I think my computer likes the size of this file. And then we were able to reconstruct sort of the stratigraphy within the column of the core of what types of particles came from where. And well, largely that's a stochastic process. We did see some systematic differences between the top core and the bottom core in terms of the abundance of regolith breccias versus impact breccias, which, since regolith breccias are formed by the gardening process, made sense. And it was still nice to see it sometimes. So. Right. Oops. So what else did we do? So we had to make thin sections. So after we were done dissecting the core, then it was time to make thin sections. Now, obviously, the thin section making process contaminates the samples for some measurements, but it actually enables a lot of other. And that's why we use the last 25%, the fourth pass, if you will, and make that material into a vacuum impregnated core. A series of vacuum impregnated thin sections. And so the problem was we hadn't done this since 1993. And it turns out if you store a bunch of stuff in Houston for 25 years, stuff goes bad. And so basically we had to rebuild the entire system more or less from scratch, including buying new saws and a new pump, and just redesigning the hardware so that we were able to once again make these vacuum impregnated cores. And it's also important to realize this is actually quite a bit of challenging. Really, I I do not have headphones. All right. I hope you guys can't hear that. Shoot. Anyway, I'm just going to talk, and if it's my assistant brought me headphones that don't work on my computer. Okay. Can somebody tell me how bad that is? Do I need to like run into the other room and try to find a set of headphones, or can people hear me okay?
It's okay, Ryan. We can hear you fine.
Okay.
Yeah, we can hear you.
I apologize.
It's okay.
The 1 hour every other week that our mower shows up is now, of course. So anyway, so they redesigned the whole set. They spent a few months relearning how to get the epoxy to both fully impregnate the core and then harden, because that's a challenge to get a column or this large a mass of material to fully vacuum impregnate. And so you can see Jeremy and myself, and then that's Jimmy Holder, who had made thin sections for us back in the 70s and 80s, and we brought him back, and he helped us with the whole process. And so ultimately it was really successful. And here you can see the finished cores with before they were cut and then after they were cut, and the first sort of the rough draft, if you will, of the thin sections. And so where we cut was also informed by the CT scan again, because we were able to scan this entire potted butt and then choose, rather than just sort of evenly spacing the cuts, to choose places that would either intersect or not intersect with things we wanted. And so that was really great. And then Jeremy was able to use the new Keyens microscope we have to take these really nice high resolution plain polarized lights. I don't know if you like green glass or orange glass better, but you get both in this one, and cross polarized reflected light. And so we're able to not just provide the thin sections to folks, but provide these detailed images as well. Okay. Right. So that was, that was the stuff that we did more or less by ourselves. Like, we don't ever work by ourselves. We always work with folks, and, the folks we're getting the samples ready for are always part of that process. But now it came time to do something that was wholly new to our experience, which was gas extraction on a sealed vacuum container. And so this picture of 73001 here on the bottom shows the metal knife edge seal that was brought to the moon, had a drive tube inside of it, and 800 grams or so of regolith, secured inside of it. And, that doesn't have a valve on it, nor does it have a way to, pump down once it's back. So when it got brought back, it was put into this larger outer vacuum container. And that happened in 1972 and basically sat in our vaults for 50-ish years before we tried to get the gas out of both the outer vacuum container and the inner vacuum container. Now, we didn't have something sitting on the shelf for this. No one had something sitting on the shelf for this. So we worked with the ANCSA science team, and they designed and built for us that's the gas extraction manifold you see there. And so here's Alex and Olga, who I think were the primary architects, it's fair to say, of the gas extraction manifold itself. And then Rita Pariah at WashU, she also played a big role, especially in the types of containers and others, and what do you call it, the process for how we got the samples out. But so Alex and Olga came down, and Juliana helped, and they figured out how to take the outer vacuum container and hook it up to this gas extraction manifold, where it's a really simple process. They just pump this down to a really low vacuum, 10 to the minus 9, 10 to the minus 10 torr, and then they open the valve between the vacuum container and this, and they expand the gas into these prepared cylinders, and that's sort of how we were planning to extract the gas. And so the outer vacuum container was relatively straightforward. It had a valve on it, although, of course, we didn't have the right adapter for it. So I think what you're seeing there is Alex actually cutting the old valve off and putting the new one on. Things went really well most of the time. Here you can see Juliana not entirely happy with the vacuum system. She makes that face at me a lot. So I promised her I'd stop showing this picture too, so no one tell her. But ultimately it went really well, and we were able to successfully extract the gas from the outer vacuum container. That was the easy part, relatively easy, because there was a valve and everything was relatively straightforward. But now we had to get the gas that was sealed inside the CSVC, inside the outer vacuum container, out as well. Now, this doesn't have a valve on it. This, I think when they designed it in 1972, it was someone else's problem to figure out how to get the gas out later. And unfortunately, it was us that was the problem for. And so this is a case where we partnered with the folks at ESA, and you can see Fran McDonald here in the picture. And again, she's just one person within a larger team within the ESA within ESA who designed a piercing tool for us. So they designed this large piercing tool with a big old chisel on it. There's a better term for that, then that's what I'm going to call it. And so there was a method to take the CSVC, immobilize it inside this large vacuum manifold, and seal this on top, and then hook the now immobilized CSVC inside the piercing tool up to the same gas extraction manifold with 4 more cylinders getting ready to take the gas out, bake everything out, get it down to where we were happy. I liked it. I conveniently made it so you can't see what the vacuum is here. And then eventually we made Fran, since she was in charge of designing it, crank down on that using the torque wrench until you heard a pop, or at least we hoped we heard a pop. And sure enough, it worked. And so, and then of course, this was the moment of truth, because I made Fran do the scary part, which was to actually pierce the tube. But then I took over and took all the credit for the photo of actually turning this little valve. That's, again, one of the main I have skills. And so, but this is the moment you see where we're all looking to see if the pressure inside the CSVC actually was not 1 bar. And it turned out to be about 27 torr, which was a really good number. You know, that's about the number that it was sealed at. So others can talk to you about the details of the gas analyses, but like, this was a really successful case for us of collaborating with both, another, another space agency, as well as a bunch of folks within the science community to design and build, to design and implement a way to do part of the preliminary examination that was quite challenging. And so a similar thing here was trying to do multispectral work on the core during the dissection process. So here you can see Paul Lucy and his team, folks who brought in their, generation 1 of their multispectral camera that we mounted on the top of the core. Of the core processing cabinet. Paul is very good on his branding here. He's much better at that than pretty much anyone else I've seen. And then, but eventually, I mean, this was generation 1, and you can see it's big, and it was a little bit bulky, and it made everyone nervous. It worked really well, but having these big, heavy things on top of the glass was slightly terrifying, since the core is just sitting right down there as we're trying to measure it. And so here you can see the second generation that was used, both, but literally 3 months later when they came back for the second round. And they were able to take really nice multispectral images along the length of the core during the dissection process. And this is important because once it's dissected, you lose the ability to take those in situ measurements. And so again, we are not spectroscopists by and large in the lab. And so it was really good to have Paul and his team there to work with us, or for us to work with them, I think is a better way to put it, to take this data. And then this is always fun to show, this is after the core has been entirely dissected and we're getting ready to take it down and put it in epoxy. And so this was putting a different type of spectrometer inside of the cabinet so that they could directly measure and look for water absorption features, which you can't do through the glass of the cabinet. And so this wasn't terrifying. Again, this wasn't terrifying at all to put this big machine inside the cabinet. I made all that noise earlier about how we only put certain things inside the cabinet, and this violates it in every way. But that was fine, because again, the next step is to literally take this out and pour epoxy over it, so it couldn't hurt it. But it was really nice to work with the team to do that. So everything I've been talking about is core dissection and related to cores, but that was only 2/3 of the work that was done on ANCSA. And so I've had 25 slides to talk about that, and now I'm going to show you 3 slides about how we worked with the frozen samples. It turns out trying to do our standard processing in a nitrogen purge glove box at -20 degrees Celsius is a lot harder than we had anticipated. And so here you can see one of our existing cabinets. This is our old bandsaw cabinet that was retrofitted to work in a -20 freezer. And you would have thought, okay, well, that should be pretty straightforward. And it turns out it's not. So -20 freezer, which you can see here in the top right, is a relatively confined space. There isn't really much airflow in and out. And so if we're going to use a nitrogen plumbed cabinet at pretty high flow rates inside of here, there's a real concern about, asphyxiating people. And so the The cabinet had to be redesigned and basically stripped down to its parts and then put back together so that it didn't leak nearly as much. And we had to refresh all the materials and find materials that work. Our normal seals, our Viton seals, they don't work at -20. And so they had to find a different seal material. They had to use glass instead of polycarbonate. The normal neoprene gloves don't work. We have these polyurethane gloves, which we protect with our lives because these seem to be the last 3 polyurethane gloves in the world. But eventually, after several years of preparations, it all came together. And here you can see us pulling the samples that had been stored in a -20 freezer in a room in Building 31 North for the last 50 years, pulling them up into the cabinet, putting them into the cabinet through the airlock. And here you can see Jeremy. I meant to wipe out the lions on his hat. Anyway, but you can see Jeremy doing what's essentially the normal sample processing, just at -20. And again, it didn't work perfectly. It turns out if you breathe on the cabinets, it was a problem, but we think we kept the sample safe. Jane Nielsen and her group did organic measurements on the samples that came out of the freezer, that had been processed that way. And I believe she got more or less the same answer as she got for our normal samples. And so this was a temporary way we did it. This was a temporary space in a temporary lab. We have a new cold processing facility like this coming online soon, where we'll do this in a more permanent basis. But it was really successful. We were really happy, again, with how the samples all came out. And so here you can see Zoe with adding her deep insight and glasses. Those are really nice glasses. Right. So I think that's everything I want to say. At JSC, we've been doing this for 50 years, and we're going to continue to do this. We have 3 goals, really. We want to provide samples to the worldwide community in a transparent and unbiased way. We're trying to maximize the science return from each of the collections, in this case, Apollo, while still preserving a significant portion of each collection for future generations. I think careful curation of the Apollo samples over the last 55 years continues to allow important scientific discoveries to be made. And it's not just us learning about the moon or the moon and the earth. It's really about learning about the solar system as a whole. And I think the recent ANCSA project was a really good kickstart for us to start thinking about how we're going to do this moving forward for Artemis. And so we were able to relearn and learn both entirely new types of things to do. So with that, the last thing I'll say is that obviously this is a big team effort. And so here's just a few pictures of all the different people we put to work in the labs over the years. And so thanks for that.
Thank you so much, Ryan. And then what we'll do is we'll go ahead and open the floor up for questions. I guess we have Chip, if you have a question.
Yeah, I sure do. First, Ryan, I just want to thank you very much for doing this for us. I know we have a lot of people online who were just really wanted to hear a lot more about the Apollo collection and lunar samples, and you did a great job giving them all that information. The question I had is, I served on a League XMAG analysis group that were looking at, how to return, process, and eventually analyze cold samples from PSRs and cold traps. And, eventually, as you know, Artemis 3 will probably return samples unchilled. And then following that, the samples will be coming back maybe colder and colder and colder. What lessons did you learn from operating at -23 degrees centigrade that allows you to say something about operating at -100 C or 150 C, or is that possible?
Well, anything's possible if you have enough money and you have enough time to get ready. I think what we learned by working at -20 is that's pushing the limit of what you can do with humans, in shirt sleeves using basically our normal curation process. But, in a walk-in freezer, you're not going to have a -80 walk-in freezer. Jeremy's, I know you're not suggesting that. I'm saying, but so -20, it was hard. I think you could do it down to -30 or -40, maybe, as long as you hire people from farther and farther north. But, at a certain point, it becomes more about you're going to have to find a different way to do it. And so if you want to work at -80, which is another common temperature, or you want to work at liquid nitrogen temperatures, robotics or some sort of remote manipulation of the samples becomes key. And then it really comes down to storage versus processing. You store the samples one way, we do, for normal sunlit samples, and then we process them in a slightly different way. And so, there's a lot of work going into that, which, I am tangentially related to, but
yeah. And also another fact, and the real factor is, what is the important science that will be done, keeping things really in those ultra cold conditions? And do we have the instruments to make all those measurements? So one has to balance, is the science there to match the investment one has to make? Yep.
No, I agree. Have to have well-defined science goals. And then, because, if you don't have to do everything at -80 or whatever the temperature is, if you don't have to do everything at a cryo temperature, if extracting the gas extracting the volatiles is done at that temperature, and then some of the other work can be done at a higher temperature later, that might make things more simple. And so I'm not saying that's the result. I'm not saying that's the answer. I'm saying understanding whether or not that's the answer is really important as you try to figure out how to do this moving forward. And I know that we just hired some new folks here at JSC who are all working hard at this. I mean, adding them to the team of people who've been here for a while and working hard on this. Sorry.
Yeah.
Well, thank you, Chip. Any other questions?
I saw a couple of hands up.
All righty then. Well, I guess if there's no other questions and stuff, everyone, thank you.
I have another question.
Well, Chip, if you have another one.
I just wanted to give somebody else a turn. So Ryan, in terms of containers to return samples from PSRs, like the special environmental sample containers or the core sample vacuum containers, do you see the design of future containers being similar to that, or somewhat different, or dramatically different?
Well, I think, I don't think Yuli's here, but I think the answer for Artemis 3 and 4 is that they're going to be similar. They aren't going to be the same, but they're going to be similar. And so as we're bringing back things, from those first few missions sealed, metal knife edge seems to still be what they have planned, and something similar, whether it's exactly the same as the CSVC or a gas analysis sample container, probably not, but it'll be similar enough that I think you would recognize them. As they move forward to, start taking samples or trying to keep them in freezers at -80, -150, whatever on the way back, I'm not sure that I'm not sure we know to a high level of fidelity what that's going to look like at this point, either from the collection process or the containment process or the curation process once it gets back here. So I think there's still a lot of open questions at those lower temperatures. Okay. But someone who knows more about this than me might be able to give a better answer to that later.
Great.
Well, Austin, do you have a question?
Hi, Ryan. Thanks for your awesome talk. Hopefully you guys can hear me. I had just a quick question for you, because you briefly mentioned it earlier about those sample history forms. I was kind of curious about what actually happens with contaminated samples and how you guys store them, what you guys do with them. So a story I remember from when I was growing up was back in the early 2000s, some interns unfortunately stole a safe of Apollo samples and contaminated all of them, destroyed the notes. And I was just curious, what happens to actual Apollo samples that are contaminated and returned to you guys? What ends up happening to them?
Well, so yeah, that's a great question. So every Apollo sample that comes back to us is stored in our return vault for perpetuity. We're not getting rid of any. Now, they're all pretty much stored under the same conditions, which is they're immobilized in some kind of container, either one of our stainless steel or Teflon containers like we use in the Pristine lab, or, sometimes in just as simple as a little plastic box, and then they're sealed in bags under air, so the process is the same. We just use cheaper materials. Basically, we don't use Teflon. We use polypropylene bags and stuff, poly something bags. And anyway, so they get stored away. How we decide whether to reuse them or not, that's where the sample history reports come in. So if I've loaned you a sample and you've done a bunch of spectroscopy work on it and you've exposed it to air, but not really changed it any other way, and somebody else comes back and is like, I too need 5 grams of soil to do a different type of spectroscopic analysis, rather than use a new 5 grams of pristine material, as long as they're okay with air only exposure, we will reuse that same soil and send it off to them. And that's useful for a couple of reasons. Obviously, you know, the data that the 2 different labs have taken is now more directly comparable to each other. We've not used 5 grams of extra material for a measurement that didn't need it, that kind of thing. Specifically to the samples that got stolen, that's a funny story, because those were already really contaminated. Those samples were not stolen from us in the curation. They weren't stolen from the vault I showed you. They were taken from a PI's lab in the building. And so the PI had already largely heated those up to about 800 degrees Celsius and melted them and saw how they degassed. And so they were already pretty messed up before they took them. They were all recovered and they're just sitting in our vault. I don't know that we'll ever have a use for them, but I'm not sure we would have had a reuse for them had they not been stolen. So
Cool. Thanks, Ryan. Really interesting and cool.
Thank you, Austin. Any other questions? Alrighty then. Well, everyone, thank you so much for coming out today. And again, this is the last one of the year, so we will not see you guys again until next year. So I want to wish everyone a happy holidays, a happy new year, and take care. And so thank you guys so much. Have a good one.
thanks for having me, everybody. It was great to be here.